Welcome to Pre-Calculus Section 3.1 on polynomial functions. So during this lecture, you should have out your notebook and take notes on the example problems that I lay out here and any vocabulary definitions that I lay out. I've boiled it down to the essential items that you'll be asked to answer in your assignment section. So all the information in this video you're going to need to know in order to answer the questions in the assignment sections. So here we go. First thing we'll talk about is the textbook definition of a polynomial function. So here's what it generally is going to look like. So it looks a little bit crazy, but let's break it down into something fairly simple. So the basic idea is that these numbers in front, so here a sub n minus 1, etc., all the way to the n, a0, these are simply real numbers. Okay, a real number, remember, is any kind of a decimal number, a number that can be written as a decimal. All right, and then we've got these degrees here, right here, right here, right here. These degrees are what we call natural numbers, and they're always going to be positive. So if you have a negative degree, it's not a polynomial, it's another kind of a function. All right, so we won't go there at this moment. But the degrees are natural numbers. So when we talk about natural numbers, remember we're talking about the counting numbers, 1, 2, 3, 4, 5, etc. All right, so if you look at this polynomial I wrote down here, sometimes we call a polynomial p of x, and I've ordered this polynomial here in order of degree, from highest degree down to the lowest degree. The lowest degree, in essence, is your constant term, because x to the 0 power would be 1. So that would be as low as you'd go in your power sequence. And so since x to the 0 is 1, it's not going to show. So your constant term is last. All right? So a couple of vocabulary words here. Your leading coefficient is the number in front of your highest degree term. In this case, the number in front is -2, and it can be either a negative or a positive number, your leading coefficient. Okay, this is your leading term. It's the highest degree term. So your leading term is this whole thing, this whole business here, -2x to the 6. We call that your leading term. Okay, notice that you can have pluses and minuses in between the terms. So the meaning of having a minus in between the terms just means that your coefficient of this term here, for instance, is a negative number, a negative real number instead of a positive real number. This coefficient is +3. This coefficient is -2.5. So I've included some decimal numbers in this example as my coefficients to show you that these numbers don't necessarily have to be whole numbers. All right? They can be any real number. All right? Now one more thing, I want to talk about the domain of polynomial function. All right, let's talk about domain first. So let's take, for instance, a polynomial that looks like this. Okay, so that's obviously an x squared polynomial. As you can see, it has no holes, no jumps, no sharp points. It's called a continuous function. So polynomials are continuous functions. So that means here any x in this direction will lie on this graph. Any x in this direction will lie on this graph. That's what's indicated by these arrowheads on the ends. So when that's the case, we've learned this before. That means your domain is all real numbers written as -infinity to +infinity in interval notation. So that's all real numbers. So let's just draw several different polynomial functions. So we've got this one, possibly this one, maybe this one, These are all continuous with a domain from negative infinity to positive infinity. Maybe we could have this one. So those are all examples of polynomial functions. Now, when we're talking about the end behavior of one of these functions, you could either get down, down end behavior, up, up, down, up, or this one's down, up, but you could get, let's write an up, down one over here. So you could get up, down end behavior. So we'd be saying as x approaches either positive or negative infinity, y can approach either positive or negative infinity for a polynomial. All right, so if we take one in particular, let's just do one example real quick. I'm going to go through the end behavior fairly quickly because this is a skill we generally have already. So this particular one here, our end behavior would be written as x approaches positive infinity. I'm on the right hand side now. Then y goes up, so y approaches positive infinity. So this is my right hand side. Then on my left hand side, I'm over here now. As x approaches negative infinity, y goes down. Okay, so y is going down. Y goes down, y approaches negative infinity. Okay, so that is how you would write your end behavior for this one in the drawing here. So we've talked about domain, all real numbers, and we've talked about end behavior being any combination of positive and negative infinity for either your left or your right end behavior. Okay, so the first skill here is let's decide whether each of these examples given to us is indeed a polynomial and explain why. So if I look at the first one, I've got 4 plus x cubed over x. Okay, now what you could do is you could say that g of x is 4 over x. If I put the x under the 4 and x also under the x cubed, which is equal to 4 over x plus x squared. Okay, so the problem with this being a polynomial is that you've got an x in the denominator on the first term. So that's really 4x to the minus 1 plus x squared. So it fails in the fact that the coefficient of the first term is not a positive number, it's a negative number. All right, so number 1 is not a polynomial. All right, let's look at number 2. So let's go ahead and put that x under both of these terms individually and cancel. So we'd have 4 plus x squared. All right, and if we wrote it in descending order from highest to lowest power, I'd have x squared plus 4. So x squared is your leading term. Your degree of the polynomial is 2. Your leading coefficient is 1, and your constant term is 4. Okay, so this one is a polynomial. It fits the bill. Okay, all the coefficients are positive, and the terms are separated by plus or minus. Okay, so this is a polynomial. Okay, let's look at number 3. So when I look at this one, it doesn't make a whole lot of sense to put this binomial under each of the separate terms like we did here, because over in this problem here and in this problem here, we could potentially cancel that x in the denominator. Here you can see that that strategy is not going to play out too well here. So this one right here is not a polynomial. It doesn't fit the constraints of a polynomial at all, the definition. This is really a rational function. We'll study those in a later chapter. Right, let's look at number 4. So this one says the function f of x is the cube root of x. Let's just write that cube root as a power. So that's the same thing as x to the 1/3 power. All right. Now, if it was polynomial, the power would have to be a counting number, a natural number, 1, 2, 3, 4, and this is a fraction. So this is definitely not a polynomial function. This is a cube root function. So that's a no. Okay, number 5, we can see is an absolute value function. Well, just looking at the graph of an absolute value function, it's going to have that point that we know exists in an absolute value function. So that means it fails the way a polynomial graph should look, which is smooth. Okay, so this graph is not smooth. It may be continuous in that you can walk along it without falling off. All right, it's continuous, but it's certainly not smooth. So it doesn't have the characteristic graph of a polynomial function or the characteristic look of a polynomial function. You're not going to have absolute value bars in a polynomial function. All right, number 6, z of x is equal to 0. So if you look at the standard form of a polynomial equation, so the coefficient times x to the highest degree, and then whatever middle terms you've got all the way down to the constant term on the end. Okay, so if it equals 0, that means all of the coefficients must be 0, so that everything is zeroed out. Okay, regardless of what the powers are, if the coefficients are 0, the whole thing is zeroed out. So this is the most simple form of a polynomial. Z of x is equal to 0. So yes, that number 6 is a polynomial. Okay, let me just throw something else in there that might come up. On number 6, if you're asked to name the degree of that function, z of x is equal to 0, the way this makes the most sense to me is that the degree, the power on each of the terms is not going to play into this at all, because if the coefficients are all 0, regardless of what the degree of the x is, it's not going to matter. It's not going to show, because 0 times anything is 0. So we essentially say that it has no degree. Okay? So if z of x is equal to 0, there is no degree. Okay, if I look at number 7, if h of x is equal to a non-zero constant, really you've got the case where you could think of this x to the 0 being beside the 5, which is the same thing as saying 5 times 1, which is 5. So this one has a degree 0. That's why I like to think of that constant term as actually being equal to the coefficient of x to the 0. The x to 0 simply doesn't show. So that's why if you have a function h of x is equal to a constant number that's not 0, then that actually is a degree 0 function. Okay, let's look at a couple of these examples here. We're going to find the degree, the leading term, the leading coefficient, and the constant term. So if I'm talking about number 1, my degree is going to be my highest power, so that's degree 5. My leading term is the entire term itself there with the highest power. So my leading term, let me just call it my leading term, LT, is 4x to the 5th. My leading coefficient is the number in front, that's 4, and my constant term is negative 5. Okay, number 2, I'm going to reorder the function highest to lowest to get it in standard form of a polynomial. So then I can answer these questions. The degree is going to be 3, my highest power. My leading term is the x to the cube, x cubed. My leading coefficient is understood to be a 1 if it's not showing. My constant term is 0 because there's no number written there, no non-zero number written there, so my constant term is 0. Okay, number 3, I'm just going to rewrite it in standard form. So instead of having this denominator under the whole thing, you want to put it under each of the terms separately. So it would be 4 over 5 minus x over 5. So this is your constant minus, now write this 1/5, this understood to be 1 in front of the x. So your coefficient is really 1/5 x. And now I'm going to put it in descending order from the highest power of x. So I'd put my x to the first power term first, and then my 4/5 would be my constant term. That's going to be last. All right. So the degree is 1. Your leading term is negative 1/5 x. Your leading coefficient is negative 1/5, and your constant term is 4/5. Okay, looking at number 4, there's 2 ways you can tackle this. So the first thing I'm going to do is I'm going to expand out. I've got a cube here, so that means I got 3 of this factor here. Notice this polynomial is written in factored form. So I've got 1, 2, 3. Then I've got this one here and this one here. So if I wanted to get the polynomial itself expanded out and written in descending order, I would have to do all of this distributing, which takes a while, and there's a lot of room for error. So that's one way to do it, and it's worthwhile doing that a few times, because when you study polynomials, you end up having to do a lot of that. The other thing we could do in order to figure out, first, let's figure out what the leading term is you could take this 2x right here, and then you're going to cube it. So I've got 2x cubed. I'm just fashioning my leading term right now. Okay? And then I've got a 1x here. And then I've got a 3x here. So if I expand that out, I'm going to have 2 times 2 times 2. That's 8x cubed times 1x times 3x. So that's 24. So that's, let me count my x's. I got 3, 4, 5 x's. Okay, so my leading term is going to be 24x to the 5th. Okay, so now what I haven't done is I haven't figured out what all these in-between terms are that I would get when I expanded this out. My x to the 4th, x to the 3rd, all the way down. All right, but I can also figure out my last term pretty easily by looking at my constants in each of these factors. So I've got a negative 1 cubed times a negative 2 times a positive 2. And those don't have any powers over here on the factors, like this one had a cube. All right, now if I multiply that out, I'm going to get negative 1 times negative 2 times 2, which is equal to positive 2 times 2, which is equal to 4. Okay, so that means my last term, my coefficient, my constant is going to be 4. Okay, just to summarize then, my degree is going to be 5. My leading term is going to be 24x to the 5th. My leading coefficient is going to be 24, and my constant term is 4. That doesn't tell me anything at all about what's in between, what the x to the 4th on down terms are, and I would get that by carrying out this distributing here, but it will answer these questions here without having to go to all that trouble, which would take probably about 15 minutes, and you'd have to be very careful that you didn't make a mistake. All right? Let's return to the idea of end behavior for a polynomial function, which will help us to know the general shape of a polynomial function based on the degree of the first term. So this theorem, theorem 3.2 about end behavior polynomial functions, says that the end behavior of a polynomial function matches the end behavior of a more simple function that is just the leading term. Okay, so this and this match. So we're basically ignoring all of this when we come up with the end behavior and the general shape of the function. So let's first talk about even functions. So when I mean an even function, I mean an even degree function. I'm talking about 2, 4, 6 as your degree, your highest power. So we know something about x squared functions already. If you have a positive leading coefficient, it's shaped like this. If you have a negative leading coefficient, it's shaped like this. Okay? So this is up, up end behavior. This is down, down end behavior. And you know how to write that in its technical way. As x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches positive infinity, etc. All right, so it'll slow me down to say that every single time. We know that part already. Well, if you have an x to the fourth leading term, then you're going to have a flattened out middle with maybe some bumps, but you'll still have the same end behavior. So this is positive leading coefficient. This is negative leading coefficient. And it's the same thing for any even degree function. The higher the degree of the term, the more likelihood that the middle terms are going to cause some bumps and wiggles and flattening out perhaps in the middle, but your ends will have that either up, up or down, down function depending on the sign of the leading coefficient. Okay, when you have an odd degree function, so I'm talking about your highest power, 1, 3, 5, and 7, 9, and on, we have down up or up down behavior. So to illustrate that, let's look at the first one. An x to the first power function is a line. So if you have a positive x, positive slope, you're down up. If you have a negative slope, you're up down. Okay, so this is positive slope, positive coefficient, you're down up. Negative slope, negative leading coefficient, you're up, down. Okay, now for a cubic, you're going to have the same idea, except it's going to be shaped with a wiggle. So you're down, up. There's a positive leading coefficient. You're down, you're up, down for a negative leading coefficient. Because if you've got an x to the fifth as your highest degree of the function, you could potentially have some wiggles in the middle due to your in-between terms, but on the ends you're still going to have the same behavior, down, up for a positive leading coefficient, and up, down for a negative leading coefficient. Now here would be an interesting time to verify this on your Desmos graphing calculator as just an aside exercise if you wanted to see what those middle terms might do to the middle of your function graph, while still noticing that the ends are going to still have that same characteristic behavior that's the same as your more simple function without any of those extra terms. Okay, so let's look at a few of these here, only in terms of end behavior. We already talked about the leading term, the degree, and the leading coefficient, and as well the constant term. So now we'll address the end behavior of these functions here. So in problem number 1, for example, let's just put that in descending order, highest to lowest. Okay, so I can see right here that I've got my degree being 2. All right, so that's a parabolic shape. All right, so if my coefficient is negative, that means it's going to be facing upside down. So this is a downward facing parabola. So my end behavior, I would say, as x approaches negative infinity, y approaches negative infinity. Okay, so that's down on the left. On the right-hand side, as x approaches positive infinity, y approaches negative infinity. So we call this down, down behavior. Okay, let's look at another one of these. Let's look at number 2. So my leading term is 3x to the 5th. So that's an odd function with a positive coefficient. Okay, so that means my odd function with a positive coefficient is going to have down-up behavior. These middle terms here might cause some wiggles in the middle. Okay, but you're talking about your end behavior here. So that's down up as x approaches negative infinity, y goes down, y approaches negative infinity. As x approaches positive infinity, y goes up, y approaches positive infinity. Okay, so this is down, up, odd function with a positive leading coefficient. Okay, so we'll go quickly through a few of these. So let's look at number 3. Okay, so this is my leading term here. So I've got a negative coefficient. I've got an even power. So that's going to be down, down. All right, and then I look at number 4. My leading term is this one. So it's got a negative leading coefficient. It's got an odd highest power. So that means it's going to be up, down. All right, and then let's look at number 5. So my leading term is here. Okay, so it's got an odd degree. 17 is an odd number. It's got a positive coefficient. So positive odd behavior is down, up. Okay, number 6, my leading term is here. Okay, I've got a even degree. I've got a negative coefficient. So that means it's down, down behavior. So that's my end behavior. Now if I look at number 7, I've got an x to the 1, 2, 3, 4. We're going to use that idea I spoke of when you don't have to multiply this whole thing out to determine what your first and last term are. Okay, we're talking about end behavior. We only care about our leading coefficient and our highest degree. So this is a degree 4. So that's even. Degree 4. So this is an x to the 4th function. All right, and my coefficient is 1 times 1 times 1 times 1. So that's an even power positive function. So even positive means my end behavior is going to be up, up. This is for number 7. Up, up. All that from knowing the first term of this function. Okay, let's look at number 8. Okay, and that's use that same idea to figure out what my leading term is. So I've got negative t squared. So I'm going to have this one here multiplied by that, and then this one here multiplied by that, and that's going to give me my highest power, my highest degree. And that's going to be my first term if I put it in order. So I've got negative t squared times negative 5t times t squared. So that's negative 1 times negative 5, that's 5. 5 times 1, so my coefficient of my highest order term, highest degree term is going to be 5. And then I've got t squared times t, that's t cubed. T cubed times t to the squared is t to the 5th. So this is a positive odd function. A positive odd function is going to have down-up behavior. Okay, so that tells me my end behavior. As x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity. Okay, the last one I'm going to do here is 9. So let's use that same strategy. I've got to find my highest term, my highest power term. I'm going to take this one times this one times this one, which is going to be squared. So I've got negative 2x cubed times x squared. So that's going to be negative 2 times 1. So my leading coefficient is negative 2. The degree of my first term, my highest degree, my highest power, 3 plus 1 is 4. 4 plus 2 is 6. So this is an even with a negative leading coefficient, which means it's going to go down, down. Since it's a 6th order term, a 6 is the highest power, it could potentially have a lot of other terms, so it won't be generally smooth like that in the middle. It'll be more like some bumps and stuff going on in the middle there. But when you're talking about end behavior, we're talking about down, down. Okay, so that pretty much covers end behavior based on the leading term, the first term. So we're going to talk about the idea of multiplicity in as simple terms as possible. So multiplicity refers to the exponent on the factor. If it's not showing, then it's understood to be a 1. Okay, so we look at the 0 of the factor. So the 0 of this factor, x plus 3 squared, is negative 3. The 0 of x minus 4 to the first power is 4. So what we would say is that we have a 0 of negative 3 with a multiplicity of 2. Here we would say we have a 0 of 4 with a multiplicity of 1. Okay, the next idea is, what does that multiplicity tell you about the shape of the graph? What is the role of multiplicity? Okay, in as simple terms as possible, if this is an even number, if the multiplicity is even, then your graph will touch the x-axis at that 0 and turn back around the other way. It won't cross over. So sometimes we call that touching, bouncing, rebounding, but it doesn't cross the x-axis. It turns around and goes back the other way. The graph does. Now, if the multiplicity is odd, as in this case, 1 is an odd number, this tells me that at this 0, the graph will cross through the x-axis like a line would. Okay, so this is a cross, and this is a touch. If m is even, you touch. If m is odd, you cross. Now let's illustrate that with a simple example. Okay, so on the first factor, my 0 is negative 3. It has an even multiplicity, so that means we touch and we bounce back off. For the second factor, my 0 is 4. It has an odd multiplicity, which means we cross over the x-axis. That would be like a line. Okay, now let's see how we start going left to right. For that, we need to know the degree of the polynomial. All right, so the degree of this polynomial here is x squared times x, that's 3. The degree is 3. My coefficient in the front here is positive, so we know that that's down, up. Okay, so that'll help me with my graph. Okay, so I'm starting, let me put my zeros on. I've got a 0 at negative 3. I've got a 0 at 4. Okay, so I'm going to hit that negative 3, and I'm going to bounce. Let me scoot it up a little so I can draw on it. Hit that negative 3, and I'm going to bounce. And I knew it came down from down on the left for end behavior purposes. Right, now when I hit 4, I'm going to cross. So there's going to be some connection that has to occur here. And then I go back out on the other end. So I meet the end behavior of being down, up. Let's do one more example on multiplicity. So here we've got a 0 of 0, multiplicity 1. So multiplicity 1, that's an odd multiplicity. That means we're going to cross. Here we've got a factor of negative 2 with an even multiplicity, 2. So we're going to touch. And then on the last one here, I've got a factor of 4 with an odd multiplicity. So that means we're going to cross. If I count my x's, I can determine the highest degree, which is the power of your first term. So I've got 1, and then I've got 2, and then I've got 3. So that's 3 and 2 is 5, plus 1 is 6. So this is a degree 6 function. And it's got a positive leading coefficient. So that's a positive up, up. So up, up. All right? So that's an even degree with a positive coefficient. So we know it's going to be up, up. Okay, so that's enough information to sketch it. So let's put on our zeros. All right, and now we're going to go left to right. So we're starting from up, and then we hit the 0 of negative 2 first. At negative 2, we're going to touch. Touch. All right, so there's a connection we got to make right here. We don't know exactly how it looks, but this is just a sketch. Okay, the next 0 we hit is 0 itself, and it says here that we're going to cross because of this multiplicity of 1. So we're going to cross. So we got to have a connection here, physically speaking, to make this graph connect. All right, and then we get to the 4, and it says we're going to cross because of the odd multiplicity, and then we're going to go up and out to meet the end behavior. So we're going to cross. So there's a connection that has to be made here, and then the end behavior that we know of because it's a degree 6 positive coefficient. All right, and that's a rough sketch of our graph based on knowing the degree, the leading coefficient, and the multiplicity of the zeros. Let's take a look at this example here that says find a formula for the polynomial p of x with these conditions. So we're told that the degree is 4. The root of multiplicity 2 occurs at x is equal to 2. Roots of multiplicity 1 occur at x is equal to 0 and x is equal to negative 4. And the graph must pass through the point 4, negative 384. Okay, so let's set up what our polynomial is basically going to look like. So that means p of x. Okay, taking the idea that the degree is 4, that means the highest power is going to be 4. The leading term is going to have a degree of 4. Okay, so the root of multiplicity 2 at x is equal to 2 means you're going to have a factor of x opposite sign 2 with a power of 2. All right, so let's put that here. X minus 2 squared from that second bullet point. All right, and then let's get to our third bullet point here. Roots of multiplicity 1 at 0 and x is equal to minus 4. Well, anytime you have a root of 0, that's just a factor that looks like a plain x, which in essence really is x minus 0, but we never put that x minus 0 on there. We don't really need it. Okay, it's got a multiplicity of 1. That also we don't have to put there. And then we've got a root of x is equal to negative 4 with multiplicity of 1. So that's x opposite sign, so that would be plus with a multiplicity of 1, and we don't have to put that either. All right, so we know we have that. Now usually you put the plain x factor out front there, All right, so and then let's put x plus 4 last. Okay, now let's utilize this last idea here that says a graph that passes through the point 4, negative 384. 4, negative 384. So this is an x value, of course, and this is a y value. Okay, now we're going to use that to find your leading coefficient. Okay, so without any knowledge about a point that this graph passes through, then you would have to make an assumption about the leading coefficient just being 1. That would be the simplest polynomial that you'd be able to come up with, not knowing anything further about a point that it actually passed through. So what we're going to do here is we're going to, instead of saying that there's a 1 in front there, we know something about that coefficient. So I'm going to say, let's call that an A. All right, let's call that an A right here. All right. So now I'm going to utilize the idea that we know when x is 4 that the value of the function y, or p of x, has to be negative 384. So if I plug in 4 for x, everywhere you have an x, so I've got a times 4 minus 2 squared times 4 plus 4 if I plug in x, and that's going to have to come out to negative 384. All right, so let's simplify that a little. So I've got 4a, so 4 minus 2 is 2, 2 squared is 4, 4 plus 4 is 8, so that's equal to negative 384. All right, so let's just keep simplifying here. So I've got 4 times 4 is 16. 16 times 8, that's 128. So on the left-hand side, 128a is equal to minus 384. So I'm going to solve for a here. So that's a is equal to negative 3. Okay, so this is my leading coefficient. All right, so if I write my final function out, I'm going to have, so I wrote it out. So I substituted negative 3 in for a, then I just wrote all this out beside it. Okay, so this is my function p of x, which meets all of the 4 conditions above. So the point here that you're given is used to find the leading coefficient. Okay, let's do another example similar to that. So this time we have a degree 10 function. We are told that the leading coefficient is 1, so instead of being given a point to figure that out, we're already given the leading coefficient. Root of multiplicity 4 at x is equal to 0. Okay, so let's see what that means. Root of multiplicity 4 at x is equal to 0. So remember, when you have a 0 of 0, or a x intercept of 0, that's a factor of x. A multiplicity of 4 means I've got an x to the 4th factor as part of my polynomial. So a root of multiplicity 2 at x is equal to negative 12 would mean I have a factor that is x opposite sign 12 with a multiplicity of 2. All right, that's another factor. And then the last one says I have a root of multiplicity 4 at x is equal to 9, which is the 0. So that would be x opposite sign 9 multiplicity 4. All right, so let's write out p of x. So we've got a leading coefficient of 1. I'm just going to put that there. Then I'm going to put my x to the 4th. And then I'm going to put my x plus 12 squared. And then I'm going to put my x minus 9 to the 4th. All right, now it says it's a degree 10 here function. I want to count up my x values and see if that corresponds. So I got 4 x's here. I've got 2 x's here, so that's 6. and I've got 4x's here, so that's another 4. 6 plus 4 is 10. Okay, so that means this function right here, if I expanded it all out by distributing, which of course would be a lot of work with these higher powers here, that would be a degree 10 function. My first term would be a power of 10, would have a power of 10, and the coefficient of my first term would be 1. Okay, this 1 doesn't necessarily have to be written right there. Okay, so this is your answer here. P of x is equal to this function. Okay, now here's another idea. So polynomials are really cool to study because they have a lot of interesting connections and patterns that you can establish. So this slide here says, can we determine the possible degree from a graph of a polynomial? All right, so at most, the degree is equal to the number of x-intercepts. Okay, that's the highest degree possible, and we're talking about x-intercepts, so these are real zeros. When you cross the x-axis, you've got real zeros. All right, as we get further into polynomials, we'll find out that they can also have imaginary zeros, and so right now I'm talking about real zeros. Okay, so at most, the degree is equal to the number of x-intercepts, and it could be less, because you could have a 0 with a multiplicity. All right? So at most, the degree is 1 more than the number of turning points. And I'll show you what that means as a picture. And then, of course, we already talked about if you look at the end behavior, you can determine whether the degree is even or odd. So let's look at a few graphs and see how these ideas make sense. Okay, so let's use the turning point idea and look at a few of these graphs here. So here's a turning point here. So that means I'm going down, and then I turn around and I go up. That's what we call a turning point. And here's another turning point here. So see, I'm going up. Now I turn around and I go down. So I've got 2 turning points. So that means my max degree is equal to 2 plus 1, which is equal to 3. All right, so this is just strictly using the idea of the turning points here. All right, and if I look at this one, I've got 1 turning point. Okay, so I've got 1 turning point, so that means my max degree is equal to 1 plus 1, which is equal to 2. Okay? So we know that makes sense because this is a quadratic and they do have a degree of 2. And let me just remind you, there's a lot more we can tell from these graphs about what the function looks like, but right now I'm just dwelling on turning points. So here's a turning point here. That's 1, 2, 3, 4. So there's 4 turning points. So that means the degree of my function, my max degree is equal to the number of turning points plus 1. So it's 5. Okay, that makes sense because this is an odd function. It's got up-down behavior. Okay, just looking at turning points again, what is the max possible degree of this function? 1, 2, 3. Okay, so the max degree is equal to 3 plus 1, which is 4. Okay, and that makes sense. This is an even function, up, up. Last example, so there are 0 turning points. Okay, so 0 turning points. So your max degree of this linear function is going to equal 0 plus 1, which is equal to 1. Of course, we know that a linear function looks like this, so it does have a degree 1, so that makes sense. Okay, so we can tell what the maximum degree of a function is by counting the number of turning points. So I want to go through this example here where what we're going to do is use a sign chart like we used when we were trying to determine the inequality, these solutions to inequalities, whether a graph lied below the x-axis or above the x-axis. But there's another application for the use of a sign diagram, and that is getting a rough sketch of a polynomial. The first thing you do is you figure out what your real zeros are, and your real zeros are your x-intercepts. Okay, so if I look up here at my function, I've got a real 0 for x cubed of 0, for x minus 3 squared would be 3, x plus 2 minus 2, and let's look at this one here, this factor x squared plus 1, where does that equal 0? So that would mean x squared must equal negative 1, and if I take the square root, I'm going to get x is equal to plus or minus I. Okay, so this is an imaginary root or imaginary solution or imaginary 0, and those are not x-intercepts. Okay, so imaginary roots are not x-intercepts, so I don't have any crossing going on associated with that piece of my polynomial there. Okay, so I put my zeros on my x number line in order, left to right, and I wrote on my intervals between my zeros, and I'm going to determine the sign of my polynomial using a test x value, and that'll tell me whether this portion of the graph is, if it's positive, it's above the axis. If it's negative, it's below the axis. So that's true for any test x that you choose within the interval. So the selection of a test x is arbitrary in that it only has to be any number that lies within that interval. So for instance, if I'm picking out test x's, so that's what I'm going to do first, test x, and then from there I'll plug it in and I'll figure the sign of f of x, basically the sign of the function. All right, positive is above the axis, negative is below the axis. All right, so the test x that I'm going to choose for the first interval, -3, then -1, then 1, then 4. So somewhat arbitrary, but it has to be within that interval. All right, so when I take that number, -3, and I substitute it wherever I have an x, and I'm only interested in the sign, so the factored form is pretty easy to use to figure out the sign because basically you're just multiplying 4 numbers together, all right, that you get by plugging in the actual value of your test x. So let's do that. So I'm going to plug -3 in here. So that's negative times negative times negative. So I'm going to get a negative for that piece. Then here I've got -3 minus 3, that's negative. Squaring a negative gives you a positive, so it's positive for that piece. And then this one here, -3 plus 2 is -1, so that's a negative. And then the last piece, here I've got a square of a negative plus a positive, so this is a positive plus a positive, so that's always going to be a positive number, that last piece. So for all cases, this last piece is going to be a positive number. All right, now if I multiply a negative times a positive, I get a negative. Then times a negative gives you a negative times a negative, so that's a positive. So positive times a positive is a positive number for the entire interval. And I just carry on that way for each of these intervals. So if I plug in -1 into my function, I'm going to get a negative times a negative times a negative is a negative again. So that's a negative. And then here, that's a negative squared. So this is always going to be positive here. And then third one, I've got -1 plus 2. That's a positive number. And then the last one we said was always positive. So I've got positive times positive times positive is positive. Positive times negative is negative. So this whole interval should be below the axis. All right, so moving right along, I'm going to substitute this 0 of 1 in, so that's positive. Then this is squared, so that's positive. So I've got 2 positives so far. And then this third one here is going to be 1 plus 2, that's positive. And then the last one we said is always going to be positive because of that square. So I've got 4 positives, so that part is positive, which means it lies above the x-axis. So lastly, I've got 4. I'm going to substitute my test x in here, so that's a positive cubed would be positive. And then this would be 4 minus 3, that's, well, it's squared, so it's always positive. And then this one here would be positive. 4 plus 2 is 6, so that's positive. And then the last one is always positive. So 4 positives again means this piece of the graph also lies above the x-axis. Okay, so that's enough to make a rough sketch knowing the zeros and whether the piece of the graph lies above or below the x-axis. Okay, so I'm going to put on my zeros first. So I've got a 0 at -2, a 0 at 0, a 0 at 3. I'm going to sketch in whether it lies above or below the x-axis. So the first piece I'm saying is between -infinity and -2, and that lies above the x-axis. All right, so this is your end behavior, whatever it is. The piece between -2 and 0 lies below, and then let me look at the one afterwards so I can see whether it's got to turn back around. All right, between 0 and 3, it's above. So I have to go from being below to being above. So it's going to do something like below, above. All right, and then my last interval, 3 and between 3 and infinity, positive. So that must mean it doesn't dip down below at all. It must bounce off there and stay positive for the rest of the way to infinity. Now that should match up with whether you've got a multiplicity of an even or an odd multiplicity for each of those zeros. So let's look back at the function here. So if you've got when you've got a 0 of -2, that's an odd multiplicity, that's a cross, that matches. When you've got a 0 here of -2, let's see, we're here, a 0 of 0, I cube that, so that's a odd multiplicity cross. So odd multiplicities are cross. So we're thinking this one should have been an even multiplicity for the 0 of 3. Okay, let's look at that. Yes, it's got a multiplicity of 2, so that's a bounce. All right, so this function here is an even function. It's got up end behavior, and it matches, the graph here matches with our idea of multiplicity. It also matches with our idea of over, under, over, the sign table that tells us whether the graph lies above or below the x-axis. So that's another application of a sign diagram for making a sketch of a polynomial. All right, now I want to show you how you can do a rough sketch just taking into consideration the end behavior and the multiplicities and whether you have real zeros, which are actual dots on the x-axis. So let's do a couple of these. So let's take a look at the number 13 here and try to make a rough sketch just taking into consideration the end behavior and the multiplicities. So here we can see that let's find the degree of this function here. So I've got a 2 here, so that means I've got x squared, and then this one has a multiplicity of 1, so that means this is an x squared times x, that's x cubed. So this is an x cubed polynomial, so that's degree 3. All right, now if I look at my leading coefficient here, I have a negative. So I have a negative degree 3 polynomial. So that means instead of having, so remember a positive degree 3 polynomial has down up end behavior. All right, so if it's a negative degree 3 polynomial, it's going to go the other way. So it has up down end behavior. Okay, so we know that about our leftmost and our rightmost part of the graph. All right, so now let's look at what we know about multiplicity. All right, so we have a 0 here of 2, and we have a multiplicity of 2, that's the power. So that means we're going to just touch or bounce off the x-axis. We're not going to cross it. All right, and then for the final factor, we've got a 0 of -1 with a multiplicity of 1. So that tells us we're going to cross the x-axis here. All right, now we have enough information to make a rough sketch of this polynomial. Okay, so first we're going to put on our zeros. So we have a 0 at -1 and a 0 at +2. And those are places where the graph will actually touch the x-axis or go through the x-axis. All right, so now looking at our end behavior, we know that this graph has to start up. Okay, and that's over here. So we know it's got to start up. What happens at -1 here? So this is -1 and this is 2. All right, so at -1, I'm going to cross. All right, so my graph is going to cross. So it starts up and it crosses. All right, the next thing I want to look at is what happens when I get to 2. So at 2, it's going to just bounce off or touch. It's not going to cross. So that means somewhere down here you're going to have a turnaround. But we're just doing a rough sketch. We're not putting on that actual value there. And then after 2, that means I've got my end behavior on the right end, which is down. And it's going to go down like that. So that's a rough sketch of my graph. All right, so let's do an even function here. Let's do number 17. All right, so how do I know this is even? I know it's even because I've got a 2 and a 4. That's a 6. So this is an even function. Okay, so an even function with a positive leading coefficient is an up-up function. All right, so I know that about my graph already. All right, now if I look at my zeros, I've got a 0 here of -5. With a multiplicity of 2. All right, so if I have a 0 of -5 with a multiplicity of 2, that means I'm going to touch and I'm going to, so I'm going to touch at -5. All right, and then the next factor says I've got a 0 of 3 with a multiplicity of 4, so that's an even multiplicity, so I'm going to touch there as well. All right, now let's see how that would play out if I try to make a sketch here. So first I want to put my zeros on there, so I've got a 0 at -5. Whoops, I made a mistake here. This is 3. And I've got a 0 at 3. All right, so I've got a 0 at 3. -5 and 3, so I'm going to put a dot for that 0 and a dot for that 0. All right, and then I know that according to my end behavior for an even function being up, up with a positive leading coefficient, it means I'm coming from here and here. All right, now for my 0 at -5, that's just a touch, so I'm bouncing there. All right, and my 0 at 3 is also just a touch, so I'm bouncing there as well. All right, and somehow these have to connect, and we don't exactly know what that part of the graph looks like exactly. But this is a rough sketch. All right. So so I use my knowledge of multiplicity and what my degree is and what the sign of my leading coefficient is to get a rough sketch. Okay, so I'm going to do one more, and this will be the final thing that I do. All right, let's do 18. All right, so 18, let's look at the zeros. I got a 0, of 2, and negative 2. All right, those are all touches because I've got multiplicity of 2, 2, and 2. All right, so the degree of my function now, I've got 2x's, 2x's, and 2x's. That's 2, 4, 6. So that's a degree 6. Degree 6. All right, and then I've got a positive leading coefficient. All right, so that means that's an even function with a positive leading coefficient, so it's going to be up, up. All right, so putting on my zeros, 1 at 0, 1 at 2, 1 at negative 2. All right, and then I've got up, up, end behavior. All right, now as far as what happens at the zeros, I've got a bounce at negative 2 or a touch. All right, so a touch at negative 2. I've got a touch at 0. And I've got a touch at positive 2. Okay, so that means if I connect all these little pieces right here, it'll look like that. Rough sketch of the polynomial. And we've done that just knowing our leading coefficient is positive. Our degree is 6, leading to up, up, end behavior. And my multiplicities are even in all 3 cases with all 3 zeros, which leads to touch, 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 or bounce, 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 whatever word you want to use, meaning it's not going through the x-axis at that point, at that 0. Okay, so that's about all for this lesson. Hopefully you took good notes and you're ready to start with the problem set. As usual, let me know when you have any questions by either taking a picture of your screen or taking a picture of your paper, and I'll get back to you as soon as possible.